Let's see this functionally complete operations. So if you are given a set of operations, are they enough to construct anything, any boolean expression? So why is this important is, we when we are designing this circuits, electric circuits, we actually want some building blocks. Building blocks means smallest parts which could be kept together so that we can form the bigger circuit, right? And in that case, what should those smallest parts be using which anything could be made? Because we don't want to end up making every circuit that is required. See, as an industry, let us say you have a industry which is making the circuits. Now you don't want to take orders from the customers, and for every order, for every expression, you don't want to build a special circuit. What you could do is, you could build at a bulk some small building blocks using which the customers will be able to put them together and they will be able to form a circuit. For that reason, we have to build functionally complete operations or functionally complete circuits, so that once you sell these functionally complete circuits, using these small circuits, they will make a bigger circuit accordingly. Now if whatever you are manufacturing is not functionally complete, then what happens is, your customers will not be able to construct every circuit that they wanted. So you should be sure that, or you should build only functionally complete parts so that they can build everything, right? Now how can we know that some particular thing is functionally complete? For that, we are going to use this theory, functional completeness. So what is functional completeness is, a set of operations is said to be functionally complete or universal. It is also called as universal if and only if every switching function can be expressed by the means of operations in it. So let us say you have manufactured a set, right? And now if that set of operations can perform every operation, which means every function can be expressed by using only that, then we can say that it is functionally complete. But how can we check it? That is very difficult, right? The reason is, you have manufactured some small building blocks and you don't know what kind of expressions that your customers want to do. Now this expression is saying that your building blocks should help your customers to build any circuit, but how can you find out what is their requirement? That is why we take a small functionally complete set which is already known to be functionally complete, and then when we come up with any other functionally complete set, we see that this new functionally complete set should be able to derive the already known functionally complete set. So for the basic step, starting point is, we already know that plus, dot and complement, these three are functionally complete. The reason is, any expression that we have seen till now, they contain only these three operators. Got it? So the set plus, dot and complement is clearly functionally complete, because whatever we write, by the definition of the Boolean expressions, they have to contain only these three operations, right? Therefore, if I give you all these three operations, you can implement any expression. So it is functionally complete. Now this set plus and complement itself is functionally complete. It is interesting. So it turns out that you need not have these three. If you have these three, the problem is, you have to manufacture three circuits, one for plus, one for dot and one for NAND, and then you have to sell them to your customers. Now sometimes they might buy more plus, or sometimes they might buy more AND, or sometimes they might buy more complement. Therefore you will end up producing something which will be left over. If you could reduce this set, that is better. The smaller the functional complete set, the lesser the manufacturing cost for you, and you could build them in blocks and there will be nothing remaining. See, it is like this. Whenever I'll just give you a small example. If you are having a car, let's say Volkswagen, and if one of the mirror is broken, and if you go to the manufacturer, the company, and if you ask for one mirror, I'm talking about the rear view mirrors on both the sides of the doors. If one is broken, they will not give you one. The reason is, if they give you only one mirror, then who will buy the other one? That is why they'll always sell them in pairs, because there is a chance that something will get remained. Similarly, if you manufacture three products like this, one product will be of high sale and other two products will be of low sale. Therefore you should always manufacture as less number of these as possible, so that there will be no leftovers. right? So we want it is always better if you could come up with only one circuit which is functionally complete, and that is what people are doing now. That is AND, NAND and NOR. These two are functionally complete. Using only NAND you can implement anything. Using only NOR you can implement anything. Therefore you manufacture, let the company manufacture lots of NANDs, and if a customer wants it, they will always going to buy only one gate. Therefore there is nothing called leftover, because you can again sell them. But there is no guarantee that if you manufacture plus this and this, someone might buy a complement in the future. We don't know that, right? That is why we are interested in functional completeness. The set plus and complement is said to be functionally complete. Why? Because I'll prove it later. So how can we prove that a set is functionally complete? I'll prove that a set is said to be functionally complete if we can derive a set which is already functionally complete. Which means if we have to say that plus and negation, if this is functionally complete, you have to using this you should be able to derive already known functionally completeness. So what is it? Plus should be able to, using these two you should derive all this. Already plus and complement is included, only thing that you derive is dot. Let's see how we can derive AND using only plus and not. A and B, it has to be derived. Now if you look at it, you could write it like this. Using De Morgan's law, you can write it like this. So if I have only two operations, one is complement and other is plus, I am able to derive AND. Therefore it is very easy to derive this one, right? So dot can be derived using these two. Therefore dot is redundant, dot can be removed. So plus and complement is enough. Plus and complement is functionally complete. Similarly, dot and complement is also functionally complete. How can you prove it? If you have to prove that dot and complement is functionally complete, then you have to derive plus. Why? Already known set is plus dot and complement, right? Then how can you prove it? A plus B, it can be written as, using De Morgan's law, A dot B complement whole complement. So we are able to write plus using only dots and complementations. So what can you say? That dot and complement is functionally complete. Plus and complement is functionally complete. Now see, it is like NP completeness theorem. We have a basic problem, from that we convert it to some other problem, and from that we keep on converting to other problems, right? Here also we have a basic set which is known to be functionally complete, which is plus dot and complement, and from this we derive two more sets. One is plus and complement, which is functionally complete, and other is dot and complement, which is functionally complete. Now from this you can derive others to be functionally complete. How? If any set is given, you now prove that it is able to do either plus and complement or and complement. If you can prove this, you can say that that particular operator is also functionally complete. Got it? So now if given any other set, you need not check plus, dot and complement. You can just check plus and complement or dot and complement, because they are already known to be functionally complete. Got it? That is the proof we are going to use. The proof is, given any set, we use the existing set and we convert it into that, right? Fine.